This is Pre-Calculus Section 1-4, Translating Graphs. You should be on page 11 of your packet. What we're going to look at today is different functions and how we can translate them or move them around, change what they look like. So we'll be reflecting, stretching, and shifting. All right, this is what, these are going to be the parent graphs here. What I'm going to do is go ahead and show you the sketch of each of these, and that way we can always go back and compare them anytime we're trying to do any of the reflecting or stretching. All right, so y equals c, or f of x equals c. This is just a horizontal line there. C is a constant. F of x equals x. This is simply just the line. Y equals x, slope is 1, intercept is 0, so there it is. F of x equals absolute value of x. This is the absolute value function here at the origin where the V shape there, right, cutting both those quadrants in half. F of x equals x squared. This is our parabola, and our standard parabola here starts at the origin and looks like that, our U shape. Our cubic function, x to the third. Here's our x to the third, constantly increasing, approaches the origin and then continues up into quadrant 1. And finally here, our square root function. Square root function looks like this. This is the parent graph starting at the origin and going to infinity and to quadrant 1. All right, so that's what those graphs will look like. And so what we're going to be doing is talking about what kind of operations will change where those graphs are located or what they might look like. If you want to go ahead and go to page 12 of your packet. Reflecting graphs. The following changes in the function y equals f of x will produce the stated reflections in the graph of y equals f of x. All right, so if you have a function here, h of x, and then it is equal to the opposite of a function, or the negative of, then that's reflecting across the x-axis. Okay. If you have an h of x function that's equal to f of negative x, then that's going to be a reflect across the y-axis. Let's go ahead and look at a couple examples. So negative of the function is with the x-axis. F of negative x is with the y-axis. Given the polynomial, or the function x to the third plus 3, describe the reflections in the graph of f generated by the following. So here we are evaluating this function, or the function's written because of the negative being substituted into the function there at x. So since that is the case here, then this is reflecting about the y-axis. If I have my function here, which is the opposite of, because I could take out a negative and I get the original function here with the opposite of, then this is an x-axis reflection. Okay? All right, so those two things here, x-axis reflection and y-axis reflection, this would be an example of an x-axis reflection. I've got a parabola here opening up, and maybe the opposite of that would be then it opening down like this. Okay? An example of a y-axis reflection. I've got a square root function opening to the right. So the opposite of that would be it opening to the left, like that. All right, below is the graph of x squared plus 2. Okay, go ahead and you'll need to sketch this graph quickly here in order to create the next graphs. But below is this graph. So you got your this is the parent function right here. And then up, or +2 shifts the graph up 2 units. Okay. What we want to do is take and sketch the graph of y equals negative f of x. So negative f of x would be this same graph, but opening down like that, because it is going to reflect across the x-axis. So we just flip it down across the x-axis. Graphing y equals f of negative x, this negative x here means to reflect it across the y-axis. Well, if I do reflect it across this y-axis right here, it actually is going to give me the original graph. So there's my reflection line. That's it. This is the original, and this would be the reflection across the y-axis. All right, non-rigid transformation, so stretching and shrinking. A non-rigid transformation actually distorts the graph. Instead of just shifting it left or right, it distorts it. So if you are multiplying your function by a constant in front of it, or the whole thing being multiplied, two things occur. If c is greater than 1, then it's a vertical stretch. So if I have a parabola here, and I multiply it by a c value that is greater than 1, then what happens is it makes it more narrow. And they call that a vertical stretch. Okay? And if c is less than 1, so between 0 and 1, then this is called a vertical shrink. Okay? Your vertical shrink would make it wider. Okay? So this is the vertical shrink, and this is the vertical stretch. And this right here was the original. All right, so those are having coefficients in front of your polynomial, or in front of your function. All right, let's look at example 3. So here's the given function, f of x equals 1 minus x squared. Describe the graph of g of x 3 minus 3x squared, and it says to sketch both of them. Well, let's go ahead and sketch the first one. We could use just a table of values to sketch it. What you can do is, what happens when x is 0? So you've got x is 0, 1 minus 0 is 1. So you've got this ordered pair here. What happens when x is 1? 1 minus 1 squared, that's going to be 0. So that also means if I put negative 1 in there, it'll be 0. What happens when x is 2? 1 minus 4, negative 3. All right, so this gives us an idea of what the original looks like. Now let's see what the 3 does to the function. All right, well, this actually is, if I take a 3 out, it's 1 minus x squared. 1 minus x squared is the original function, so what does the 3 do? The 3 is going to give us a vertical stretch because 3 is bigger than 1. It's going to make it more narrow. Give you an example here. What happens with that is, if I put in 0, I'm going to get 3 minus 0, which is, or if I put in 0 here, I'm going to get 3 minus 0, which is 3. So we've got up 1. All right, if I put in 1, I'm going to have 3 minus 3, which is 0. And negative 1, I'd have 0. If I put in 2, I'm going to have 3 minus 3 times 4, so 3 minus 12, that's negative 9. You can see here that this graph now all of a sudden is more narrow. All right, so there's an example of your vertical stretch. All right, if you want to go ahead and go to the next part here, we've got how about horizontal and vertical shifting? When your expression is being added or subtracted to with inside the parentheses, okay, you're going to be shifting it if it's subtraction, so x minus c, you shift it to the right c units. If it's x plus c, you shift it to the left. If you're adding and subtracting outside of the expression, then you're going up and down. So down if it's subtraction, up if it's addition. So when you shift left and right, you can see here it's the opposite signs. When you shift up and down, it is not. Multiple transformations all at the same time. There's an order that you want to try to do that. Okay, first you want to graph the parent function. So first you graph the parent function. Then what you can do is reflect it. Then do the stretching or shrinking of the function. And the last thing that we would recommend is to translate it. If you do it in that order, it seems to give you a good result. Okay? You'll find this information here at the top of page 13. There's a position for you to write in each of these in order, 1 through 4. The last thing that we're going to do is actually take some graphs and do the transformations to them. Okay? So the first one we're going to do is y equals 3x. Y equals 3x. What they want us to do is to try to graph the parent function. Like, what's the parent function? The parent function is y is equal to x. Okay, so here's my y equals x. It is the line that cuts through your axis here and has a slope of 1. So there's the parent function. Okay, from there what we're going to do is describe this. Well, this means that it has a vertical stretch. I can go ahead and put a couple values in. 0 is a point. If I put in 1, I'm going to have 1, 3. So there's the stretch to it. If I put in -1, I would have -3. Table of values always works to be able to graph. Okay, so there it is. Okay, so this y equals 3x. The parent function is y equals x. It's a vertical stretch because of the 3 is greater than 1. All right, let's go ahead and look at the next example. Y equals x minus 3. So the parent function is y is equal to x. The minus 3 means it's going to be shifted. It also shows us that the intention was to write it as x minus 3 like this. It won't matter either way, but that's shifted to the right 3 units. So let's graph the original. Here's my original parent function. Got an ordered pair here, 1, 1. Now if I, and 0, 0, and -1, -1. Now if I shift it 3 units to the right, that would be located here. 1, 2, 3. Same line, same slope, just shifted to the right. Okay? All right. Let's look at the next one. Y equals the square root of -x minus 2. Y equals the square root of -x minus 2. All right, well, the parent function would be y equals the square root of x. That's the square root function. Okay. This one's a little bit more different because of the subtraction in here, but let's go ahead and work with my minus sign underneath here. If I take the minus sign out, like this, negative x plus 2, then this is going to help me with determining all of my reflections and things. Okay, so the first thing that we've got is this negative. The negative here, it's f of -x. This is going to tell me that it's shifted, or it's reflected across the y-axis. y-axis. And then the plus 2 tells me that it's going to be shifted. Okay, you have to know the direction. But since it's x plus 2, it's going to be shifted left. Left 2. All right, let's go ahead and start by doing the parent function. You can always graph these in your calculator, y equals the square root, just to get the parent function if you're not sure what it looks like. There's the parent function. Let's first reflect it because we want to go in order. So you do the parent, then you reflect it if there's a negative, so that's here. The second thing that we do is any shrinking or stretching. I don't have a coefficient. And the last thing would be to shift it left 2 units. So I'm going to go 1, 2. This is my original point. There's the actual graph. Okay? So this is step 1, parent function, step 2, and then the last step here, shifting it to the left. Okay? This would be the end result. All right, I think we got one more here. -4, absolute value of x plus 3, and then plus 2. Y equals -4, absolute value of x plus 3, and we've got plus 2. So the parent function would be y equals the absolute value of x. Let's go ahead and graph that. V-shaped there in quadrant 1 and 2. All right, first thing we were going to do is, because it's negative out in front here, because of the negative, we're going to reflect it. So it actually is going to open down like this. The next thing we're going to do is because of the 4, so the 4 is going to be a vertical stretch to it. I'm going to go ahead and that vertical stretch would be, let's put some values in here. So if I had -4, absolute value of x. If I put in 0, I get 0. If I put in 1, I get -4. And I get, if I put -1 in, I also get -4. So here we go. This is my vertical stretch. And now the last thing that we're going to do is we will be shifting it. The plus 3 in here means shift it left, and the plus 2 means to go up. So from here, I'm going to go left 3, so there's 1, 2, 3, and then up 2, 1, 2. Here's my vertex, and then the same stretch would occur, the narrowness of it. So that's where it would be located. Now when you have graph paper, you'll be able to get all the parts and in the right spot. Okay? All right, so the last thing would be to say that it reflects about the x-axis. It has a vertical stretch because 4 is bigger than 1. And it's shifted left 3 and up 2. This is all compared to the original parent. All right, that is it for this section here, and this is your assignment.